be able to predict the weather precisely has always been one of man's great dreams. For centuries, he has been broadening his knowledge of the physical laws governing the weather and developing new instruments to analyze and forecast weather conditions. When radar first came into use, few foresaw that it was to have an important place in weather forecasting. At first, echoes like these were considered a nuisance, and every attempt made to eliminate them, until it was realized that they were, in fact, pictures of weather disturbances. So, overnight, aerologists found in the magic of radar a new and exciting weather tool. This is a way of actually seeing the weather, night or day, regardless of visibility conditions, up to distances of several hundred miles. With this new type of weather observation, an aerologist can locate and identify a disturbance, usually with great accuracy, determine range, intensity, area, course, and speed, and give up to 6 hours advance notice of its coming. Whatever command wants: clear areas for maneuvers, stiff breezes for launching or recovery of aircraft, calms and light seas for fueling, cloud or storm cover during action. If the condition is within radar range, the aerologist usually can put his finger on it. Radar's value in weather detection arises from the fact that large water droplets offer almost as good a target for the radar beam as a ship or land mass. And droplets falling as rain or snow are characteristic of the major weather disturbances: cold fronts, warm fronts, thunderstorms, and typhoons or hurricanes. Equally important, each of these disturbances has a characteristic echo pattern easily identified on the radar scope. Fog and wind are typical of the conditions that radar cannot pick up directly because of their lack of precipitation. However, these conditions are often associated with the disturbances that radar can see. So, radar is extremely valuable in determining their presence. Let's see how radar information is used in the case of these four major weather disturbances: thunderstorm, typhoon, cold front, warm front. Aboard this carrier, the aerologist knows there's a cold front in the vicinity. This particular type of weather can be used to good advantage by a carrier if location, course, and speed of the disturbance can be determined with accuracy. A cold front is formed by a moving mass of cold air wedging under warmer, moist air. As the surface warm air is pushed back, it is also forced over the cold air and greatly cooled. The result, in severe cases, may be rain, sleet, snow, violent turbulence and lightning, little or no visibility, and intense icing conditions for aircraft. The front shows up on the scope as an easily recognized series of small, round, bright echoes. This front is aligned in north, northeast, south, southwest direction. Thunderstorms are seen to be dispersed all along it. Further observation indicates the front is approaching at about 20 knots. This front is characteristically narrow, 10 miles and several hundreds of miles long. Activity within the front is severe. This activity can be determined from the intensity of the echoes and the height of the thunderstorms. The greater the height of a thunderstorm, the more severe it is. Scanning with increasing antenna angles indicates these storms are up to 40,000 feet. With the weather situation known, the commanding officer makes his plans. Since the carrier's planes are going out on a simulated mission, the carrier skirts the front to take advantage of the stiff breezes always found along a cold front. Prior to takeoff, the aerologist gives the pilots precise information of weather conditions to and over the target, as well as the shortest route through the front. While the planes are away, the carrier steams within the narrow band of rain and clouds as protection against visual spotting. Course is guided by scope reports. When the planes are ready to return, they're given up-to-date weather information for the trip back. Meanwhile, the carrier takes the shortest route to the most desirable recovery area. As observations go on, the front is seen to slow down and broaden, and becomes more intense as the brighter, denser echoes indicate. Observations continue until the front is no longer of tactical use to the carrier. The arrival of a warm front usually means prolonged bad weather. In the warm front disturbance, a moving mass of warm air striking a cold air mass is forced up and over the cold air, cooling as it ascends. The cooling of the warm air results in a wide band of clouds and precipitation. The aerologist wants the answers to questions such as these. What are the limits of the precipitation area? Are hidden thunderstorms present? Is there icing? Radar has many of the answers. The precipitation area is readily identified by hazy, widespread echoes. In this case, it appears that the precipitation area lies some 50 miles southwest of the carrier and is moving northeast. Thunderstorms are present, their great height making them appear as small, bright echoes. As observations continue, the speed of the front is indicated as 15 knots. With the front located and its course and speed known, the task force commander makes his decision. He's planning to refuel his force, so he remains under the cloud deck, but clear of precipitation areas. Later, after nightfall, he will run through the front, taking the shortest route as indicated by the radar reports, and will arrive in a clear area for the next day's flight activities. This is the appearance of the frontal area as the carrier begins its run through it. Although visibility is very poor, radar safely guides the carrier's course. At this Naval Air Station, violent local thunderstorms are in the habit of showing up suddenly between reporting stations, just when and where being anybody's guess. Of course, the station's aerologist studies all available weather reports diligently, but he's found the real answer to his problem in keeping his electronic eye peeled. These local or air mass storms are often triggered by a mass of warm air rising as it pushes against a hill or mountain slope, causing severe up and down drafts. Lightning, rain, and possibly hail. When the aerologist sees an echo like this, small, bright, but fuzzy-edged, he identifies it as the intense, isolated precipitation area characteristic of a thunderstorm. In this case, range is 60 miles. Height, about 30,000 feet, indicates the storm is severe. After observing the storm for several minutes, the aerologist can determine its course as 40 degrees true, speed 18 knots. Estimating the area of an individual storm is a matter of judgment. When it's at considerable distance, the storm's base is below the horizon and therefore off the radar beam. After further observation, the aerologist switches to 10-mile range markers and determines that the storm will reach his station at 13:30 and should clear it by 13:50. Aircraft operations are directed accordingly. By 1440, he can see the storm dissipating to the northeast. Total effect of the storm on the station's operation, only 20 minutes lost in the day's routine flying activities, simply because the storm's course and severity were predicted by radar. The weather station at a small Pacific anchorage receives a tropical storm advisory. A disturbance relatively mild, with winds up to 45 knots, has been reported. The station aerologist plots the estimated position, course, and speed of the disturbance. The storm apparently will pass well clear of the anchorage. The commander of a task group in the anchorage is informed of the whereabouts of the disturbance. From a base along the path of the storm, a weather reconnaissance plane goes out to look things over. Back at the weather station, the weather is worsening, although the storm should be passing well clear of the station. Later that day, heavy precipitation echoes begin to appear on the station's PPI. Besides being intense and widespread, they are arranged in spiral rings. These spiral rings confirm the aerologist's worst suspicions. Not only has the storm changed its original course, but it's become nature at her dreaded worst, a typhoon. Typhoons are fearful cyclonic disturbances, more or less self-generating, that reach really tremendous heights. Yet, because of their very height, radar can detect them at great distances and thus give advance notice of their coming. The aerologist knows only too well what typhoon weather is like. Savage winds and rain, and ship-killing seas, up to 70 feet. Even with the typhoon's eye not yet on the scope, or when it's obscured by a wall of violent precipitation, the aerologist can calculate its approximate position from the radius of curvature of the echoes. Range, 237 miles. Course, 012. Speed, 11 knots. This indicates the typhoon is heading directly for the anchorage.
Now hear this. Now hear this. Set typhoon condition 1. Set typhoon condition 1.
The anchorage begins boarding up immediately. The storm's position, course, and speed are broadcast to all ships and stations. The commanding officer of the task group in the anchorage gives orders to get underway. The problem raised by the typhoon and its course change is simplified by radar's accurate pinpointing of the storm's position. His radar-based decision that a course of 085 will clear the storm while returning his group to station with minimum delay is based on actualities regarding the storm, not estimates. Without radar, a far more conservative and wasteful course would have been necessary. Further observations confirm the original position, course, and speed of the typhoon. As the typhoon rages, the weather station radar continues tracking it. The eye is about 20 miles wide, and the radius of the storm about 100 miles. The tight spiraling of the echoes around the eye is characteristic. Reports from weather reconnaissance planes are in now, and they square nicely with the radar observation. Observations continue throughout the entire range of the radar, for typhoons seem to have vicious minds of their own. The typhoon may suddenly change direction again, or a twin typhoon can develop and go off on a course of its own. But as long as the electronic eye is on it, the whereabouts of the typhoon is a mystery to none, its fury far less threatening to all. Thus radar has given the aerologist and the command he serves a valuable new weapon in man's age-old battle with the elements. For as long as a weather disturbance is accompanied by precipitation, it can be seen on the PPI scope, and what it is, where it is, and where it's going, determined with a high degree of accuracy. Such information, when used in full partnership with the aerologist's judgment and the long-range information provided by the weather map, helps immeasurably in minimizing the danger and maximizing the tactical benefits of major weather disturbances. Weather prediction speaks with a new authority today, for with radar, short-range weather forecasting has come of age.